Hey everybody, it's Monday, October 5th. As you can see here in the aim today, we are going to wrap up graphing translations. The first thing I want to do is talk about the problem that was assigned for you to submit on Friday. So on Friday, I posted this problem under the classwork tab, and I asked you to take a look at it and sketch, as the instructions say, to sketch a possible velocity versus time graph given the acceleration versus time graph for the same interval. And so, as I mentioned in the instructions for that assignment, there is no one right answer for this. So there are a lot of assumptions that you can make that would inform how your graph looks. But there are a couple of things that we should point out about this. The first thing that we should point out about this is that here, there's no acceleration. And the question that we have to ask here is, how exactly do we interpret that in terms of what that's going to mean for the velocity versus time graph? And as we said the other day, when you're going backwards, that means from a graph of acceleration to a graph of velocity, or from a graph of velocity to a graph of position, you should think whatever is happening to this graph, in this case acceleration, should be happening to the slope of the velocity graph. Notice then, before we actually do this, that's the reasoning part. The slope of the velocity versus time graph represents acceleration. And we can write a little more about that, but that's the idea. So again, whatever is happening to the acceleration should be happening to the slope of the velocity versus time graph. So because the acceleration is 0, that means the slope of the velocity versus time graph should be 0. Now, some of you might have been confused when I said, feel free to make whatever assumptions you want because there is no correct answer. The real issue comes down to the answer to the following question. What's the initial velocity of this object? Is it 0? Is it positive? Is it negative? It doesn't actually matter. And that's the point. You can decide that. I'm going to decide, to make my life easy, to make the initial velocity 0. And so that's got to be about that long. And so that looks about right. And so again, we can check the slope of the velocity versus time graph is 0. That means the acceleration should be 0. And the acceleration is 0. Cool. Okay. So in the very next instant of time, we have a very short positive acceleration. And we can tell it's positive because it's above the x-axis. So the acceleration is 0. It jumps up to positive for a very brief instant. And then it goes back to being 0. Whatever is happening to the acceleration, positive for a brief instant, should happen to the slope of the velocity versus time graph for a brief instant. So I'm going to make the slope positive for a brief instant. Notice that's about it because it's not a very long amount of time. So I'm going to make the slope positive for a very brief instant. And then it's got to be 0 again. And that's for a while. Maybe a little longer. And that seems about right. Now, the next section here shows a very short positive acceleration again. So I'm going to make a very short positive acceleration. And then it's 0 again. Okay, so that's step 1. Remember, you make your sketch. But it's important to realize here, if we call this one A2 and we call this one A1, it should be clear to everybody A2 is way greater than A1. And so that means the slope during that second segment should be larger than the slope during that first segment. And so the way that we can do that is pretty simple. We just have to make the line a lot more slanted. And so it should look something like that. The velocity grows by more in the same amount of time. And then constant again. And that's it. Now, it's important to realize you can have the same sort of thing down here, assume that's horizontal, or from up here. But the idea is you're free to do that however you want because they don't give you any information about the initial conditions for the object. So that's what that one should look like. And so for that run, just to write something a little better for the explain your reasoning part, we can say here, since the slope of the velocity versus time graph represents the object's acceleration, whatever is happening to the acceleration should be happening to the slope. Velocity versus time graph. And that's the idea. If you remember what the slope of every graph means, and remember what the area under the curve for every graph means, these don't end up being too bad. Okay, so I'm going to have you try a few more of these on your own. But before we do that, I just want to talk about one more example that's frankly particularly annoying. And so this one is in the one-dimensional motion packet. It's page 17, number 22. And if you notice, there's just a lot going on here. And this particular problem, we're going to take the position versus time graph that's given to us, and we're going to draw the velocity versus time graph. Now notice, the position versus time graph is curved at certain spots. And wherever it's curved, that means we're going to assume that the acceleration is constant. When you see complicated examples like this, I think the first thing you should do is just get a sense of what's happening here. So if we do that by just thinking about like what the slope of the tangent line is going to look like, notice the slope of the tangent line is increasing. Then it almost looks like for a brief instant, it's constant. And then notice it actually starts to curve down again. So the slope of the tangent line begins to decrease until time 3, where the slope of the tangent would be 0. So the object is stopped here from T3 to T4. Then the slope of the tangent line begins to increase again in the negative direction. It almost looks constant there, but you can still see there's a curve to it. And then it starts to level off again. So the slope of the tangent line is going to get more horizontal until the object stops again. So doing this first will give you just a pretty good sense of like, okay, it speeds up, then it slows down, then it stops, then it speeds up, then it slows down, then it stops. Because that's going to be helpful. So when the problem is annoying like this and there's so many segments, I suggest you do two things. The first thing I suggest you do is you copy the graph out of the packet and you put it on your piece of paper. And the second thing I suggest you do is you take those lines that they give you for T1, T2, T3, and so on, and you extend them down to your velocity versus time graph. What I mean by that is you do something like this. So you take a straight edge and you extend those lines down so you can give yourself a little bit of some guidelines to make this easier for you. So as we said, this is going to be a velocity versus time graph. So we'll set this up and we'll make an attempt to answer the question. So here, they told us that the velocity, because of the slope of the tangent line, again, let me go back to that, the velocity is increasing here because the slope of the tangent line is increasing. And so we want to draw the velocity increasing from 0 to t1. So from 0 to t1, we're going to go ahead and we're going to have our velocity increase. Again, you can make an argument that this should be curved, but since we're going to assume the accelerations are supposed to be constant, we're just going to make the line straight. Okay. So now notice the second T1 happens, while it looks straight for a second, it's really already starting to curve back down here in the region from T1 to T3. The slope of the tangent line is decreasing in magnitude because it's starting to level itself out already. It's curved the whole time, so that's just the way it works. And so from T1 to T3, the velocity should be coming down. And so it should really look like that. Now this is hard to do on here, so I hope you bear with me, but it should basically just be a triangle. And so I'll try to do that one more time quickly. It comes up like this, and then it comes down like this. I'll just color those in to try to make them as straight as possible. And that's that. So notice now we've already gotten to T3. Well, as we said earlier, what happens at T3 is that the velocity is now completely zero because the slope of the tangent line is leveled off. And that happens all the way to T4. So from T3 to T4, we're just going to make the velocity zero. We got a zero velocity there because the slope of the tangent line of the position versus time graph is zero. So we just color it in. We make sure we distinguish it from the axis. Of course, mine was red, so I didn't need to go this nuts, but you get the idea. And then now that we've reached T4, the slope of the tangent line is increasing, but it's increasing in the negative direction. And it increases in the negative direction up to T6. So the velocity should be increasing up to T6. And then notice after T6, the slope of the tangent line starts to decrease because the line is leveling off. It's getting more horizontal. Whoops. And so it should come back down to zero like that. And that's it. We see basically some symmetry in this graph. It speeds up, slows down, and then speeds up and slows down in the other direction. Now, drawing the acceleration graph would be fairly simple. It's not really asked for in this question, but we can just talk about it as we're wrapping this up. So notice the acceleration versus time graph. Remember, this was a velocity versus time graph. The acceleration versus time graph can be figured out just by looking at the slope of the velocity versus time graph. So the slope starts positive, then goes negative, then is zero, then is negative, then is positive, right? So we have a positive slope here, then a negative slope, then a zero slope, then a negative slope, then a positive slope. So we should see positive up to T1. So that would be T1. Then it's going to come all the way down here, discontinuous function, and then it's going to be negative until T3. And then it'd be 0 all the way to T4. And I'm running out of room, so I'm going to make this small. Then it's going to jump back down. It's going to be negative again, and the same amount. And then that would be up to T6. And then at T6 again, it jumps up as being positive and same as before. And that's it. So you're just looking at the slopes of the tangent lines and taking these things one at a time. That's the idea. Okay, so attached to this post, the post with today's video in it on Google Classroom, you will see a worksheet which has the name Graphical Translations. I'd like you to open up that worksheet. And when you go to that worksheet, the first problem will be this one, which I assigned to you last week. The second problem is B1WWT20, which is what I want you to do now. So this graph says velocity versus time graph, acceleration versus time graph. And it says a student obtains a graph of an object's velocity versus time and then draws the graph of the acceleration versus time for the same time interval. What, if anything, is wrong with the graph of the acceleration versus time? If something is wrong, identify it and explain how to correct it. If the graph is correct, explain why. So I'd like you to pause this video and take 4 or 5 minutes to look at this problem. I want you to look at it and see if there's anything wrong. If there's nothing wrong, then explain why it's right. Take a minute to correct and or explain why the thing is correct. And when you hit play, we'll go over it. Okay, so this problem says the kid has a graph of velocity versus time, and they're trying to draw a graph of the acceleration versus time. So I hope when you were doing this, your thought process was a little something like this. And I want to draw, so I'm just going to go back to here. That you looked at this and you said, well, that on the velocity versus time graph is a negative slope, so that means the acceleration should be negative. We go to this graph and the acceleration is negative, check. And we come over here and the slope of the velocity versus time graph is 0, so the acceleration should be 0, check. And we go to the next segment and we see that the slope of this graph is positive. I forgot to mark this over here. This is 0. The acceleration is positive, and so we should have a positive acceleration, check. And we come over here, and again, because it's a horizontal line, the acceleration is 0, and they show that on the graph, so that's good. Now, I would imagine a lot of you stopped there. But if you did that, then you only did the first step of what we're supposed to do. Because if you remember, and I'm going to go all the way back to this, second step after you're doing this is to look at the magnitude of the slope or area under the curve to make judgments about the approximate magnitude of the quantity on the new graph. So if we go back to that graph, we have to look at the size of the slopes. And I hope everybody can realize here that this is the same y-axis value. So let's just say it's 10. This graph over here on this side goes from 10 to 0 in a certain amount of time, which we'll call t1. And over here, this graph goes from 0 to 10 in a certain amount of time, which from here to here we'll call t2. And I hope everybody realizes, looking at that, t1 is a lot greater than t2. Why am I saying this? Well, if you look at the acceleration equation, acceleration is delta v over t. And that means that the acceleration is inversely proportional to the time. And so if the time is much, much smaller, but the delta v is the same, then the acceleration is going to be bigger because we're dividing the same number into smaller pieces, right? If you want to look at it in terms of the slope, the rise is the same, but there's much less run. So the acceleration in this second segment should be way bigger than this acceleration, but they show it the other way around. So really the height of this graph should be taller, like this. And that's wrong. So for the key, hopefully you wrote something like this. Since the acceleration is the slope of the velocity versus time graph, the second acceleration should be larger than the first because the same change in velocity happens over a shorter time interval. That's the idea here. It's the same change in velocity, but the change in velocity occurs in less time, which means the slope is bigger because the acceleration is bigger. All right, take a second to pause this video and write that down if you need to. And when you hit play, we'll move on. Let's just take a second to look at one more. This is on the back of this sheet. There's only one problem on there. It's B1 WWT17. It's a velocity versus time graph. And it says here, a student obtains a graph of an object's velocity versus time, and then draws a graph of the acceleration versus time for the same time interval. They're asking you what, if anything, is wrong with the graph of the acceleration versus time, and if something is wrong, identify it and explain how to correct it. If the graph is correct, explain why. So I'd like you to take, let's say, 5 minutes to look at this one, evaluate whether it's right or wrong, make your explanation, and when you hit play, we'll go over it. Okay, so on this problem here, it says a student has a velocity versus time graph for an object and then draws the acceleration versus time graph. So now we're going forwards, so to speak, from velocity to acceleration. And so because we're given a velocity versus time graph, all we have to do is look at the slope. So really what we want to pay attention to first is just the general outline for the graph. And so looking at the first interval here, we have a positive slope, so our acceleration should be positive. That's at least for this first segment here. The very first segment, the acceleration is 0. Then moving on to this flat segment here, we have another 0 acceleration. Here, we have a constant and negative slope, so that slope should be negative. Then here, the acceleration is 0. Then here, notice the slope is negative again, so we have a negative acceleration, another segment of 0 acceleration. Then we have a positive acceleration, and then we have a 0 acceleration to finish off. So our acceleration versus time graphs should match that. So coming back to here, and we'll do this in order just so we make sure, 0 acceleration, 0 acceleration, positive acceleration, positive acceleration, 0 acceleration, 0 acceleration, negative acceleration, and that's where they made their mistake. This is wrong. It's supposed to go like this, because the fact that they sped up and then slowed down means the acceleration should be in opposite directions. Notice, and this is like a small detail, but when we were talking about acceleration versus time graphs the first day when we started to cover graphing in more detail, we said the area under the curve for an acceleration versus time graph is a change in velocity. So this area under the curve here is above the x-axis, so it's positive. But since they changed their velocity by increasing it, but then decreasing it along this segment, there should be a negative area under the curve here. And notice that only works out like that if that bar is below the x-axis. Okay, moving on. And by the way, I drew this a little too short. That should be a little longer, the same height as all the other ones to there. Of course, it's got to be the same height as this one. These two have to be the same height because the increase in velocity over this first segment is canceled out by the decrease in velocity over this segment. So during the next segment here, we have 0 acceleration. And so we have 0 acceleration. Then we have a negative slope. So negative acceleration, 0, 0. And then positive acceleration, and they made a mistake again. And so we come up here, should be about that tall. And we make our little dotted lines. And that's the correction. So I think the basic idea here is that the mistake that this person made, if you zoom out and look at their overall thing, is they said, well, all the velocities are above the x-axis, so all the acceleration should be above the x-axis. And all the velocities are negative here and below the x-axis, so all the accelerations should be negative. But of course, that's not how it works. When an object speeds up, the initial velocity and the acceleration are in the same direction. And when the object slows down, the initial velocity and the acceleration are opposite directions. And so the main idea here is that to determine, especially when you have a graph, is that to determine the sign of the acceleration, all you have to do is look at the sign of the slope. Let me just show the answer key here real fast. And so your answer should look something like this. And so what I wrote here is the sign of the slope of the velocity indicates the sign of the acceleration. Since the second and fourth accelerations, so that would be this acceleration and this acceleration, are indicated by negative and positive slopes, they are actually negative and positive accelerations. So I switch this positive acceleration to a negative one, and I switch this negative acceleration to a positive one. And that's the idea. You think about what the slope means, you think about what the sign is, then you think about how large it should be relative to the other features on the graph, because all of those changes in velocity are the same, and all of those changes in velocities occur over the same time interval. All of the accelerations are the same, and because all the accelerations are the same, they should be drawn to the same height on the graph, more or less. Like I said, this is not an art contest. I am not judging you on your ability to draw. The graph is supposed to reflect general trends, but if it is noticeably different from the other heights, then that would be an issue. And so notice this one is about this tall. It's not perfect, but it's about there. And also this bar that I drew is this tall, and it's actually a little short, but again, it's just about there. That's that. The biggest issue with this one really is its width, actually, but we're not going to go too nuts about that. And with that, that's pretty much it for graphing translations. And so now, and I know it seems weird to have two aims there, especially because today is Monday. Jeez. But for the rest of the video today, we are going to talk about accelerated motion and how we can use concepts of accelerated motion when we're designing experiments. Now, depending on how long this video actually already is, which I'm not sure of because I'm still in the process of making it, we may not actually get to the real substance of this discussion today. We may end up saving this for tomorrow, but for now, this is where we're going. We are trying to think about how we can use our understanding about accelerated motion to design experiments. Now, of course, because you are not here in person, you're not actually going to be able to do the experiment that we usually do. But I actually think I do have a pretty good alternative that you can do at home. Okay, the first thing we want to talk about is the answer to this question. So in your reference table, you have an equation that says x equals x naught plus v naught t plus 1/2 at squared. And sometimes we can rewrite that like this. And so the question is, how does rewriting the equation x equals x naught plus v naught t plus 1/2 at squared as this change the way we think about the equation? I want you to take a couple seconds to think about that. What does that look like? Well, I think the main point here is that this part should look very familiar to you. When we rewrite this position equation with the x of t part, it changes the way we think about the equation because we think about it as a function. And that's a very important idea and a big difference between the way we use this equation in AP physics versus the way we used it in honors physics. So this equation is actually super useful and versatile, as you'll see hopefully in a couple of minutes here, because we can think of it as a function. And so essentially, when we write the displacement equation as this x of t form, the function form, we should interpret it as a position function. Specifically, it's a function showing you the position of an object as a function of time. And of course, what's particularly nice about that is that your calculator graphs functions. Take a second to pause this video and write that down, because that's really important. And then we're going to take a second to see how that works. Okay, so your AP reference table shows you this equation. It's not actually written as a function in the reference table, but you should always be thinking about it as a function, because that's essentially what it is. It's a function of time. Really, it's a quadratic function. And so the main point that we're trying to make here is that this equation is essentially a template for all position functions. And this part's very important, so I'd write this down. When position functions have numbers plugged in for the variables, the function always follows the template given here on the screen. The position as a function of time is equal to x naught plus v naught t plus 1/2 at squared. So the obvious question here is, well, what does that mean? And so essentially what we're saying here is, if we had an example that looked like this, x of t equals 3 meters plus 5 meters per second times t plus 3 meters per second squared, then what we're saying is that these numbers here, the 3 meters, the 5 meters per second, and the 3 meters per second squared, correspond to these variables. 3 meters is your initial position. 5 meters per second squared is your v naught t. 3 meters per second squared is your 1/2 a. And that's the idea. So by being given a position as a function of time, you always know the value of these variables because it has to follow this template. And additionally, if you know these variables about any object, then you can write an equation for its position as a function of time. And that's very important because that allows us to do a lot of things, specifically because you have a graphing calculator. So let's take a look at that. Let's say you knew an object had these variables associated with its motion. Well, you could go to your graphing calculator and go to the y equals function and type this in. So notice, let me just go back to that screen for a second. The number that's by itself is the initial position. So we put the 3 by itself. The number that's multiplied by t is the initial velocity, so we multiply 5 by x. Notice in your calculator, the button for these functions to type them in is x instead of t, but for our purposes, the t in the equation is going to be replaced by x in your calculator. And then the number that's multiplied by the t squared, or the x squared in your calculator, is 1/2 the acceleration. And so notice here that we can graph this and get it to look nice. That's a nice looking graph. So we automatically now have a position versus time graph just by knowing those variables and graphing that function. Now, there's something I want to mention here, because the graph did not initially look like that when I first put this up. It looked more like this. Well, it actually didn't look like that, but this will still enable me to make the point. If you plot the function and it doesn't look good on your calculator, you always hit zoom and then 0. So notice when I hit zoom, 0 is not in the menu. You have to scroll down for it. But zoom 0 is zoom fit. And so if you hit zoom and then 0, it will replot the graph and make it look nice. And then, of course, because I zoomed in, it kind of messed with it. But if you did zoom fit without doing that, it would just give you the nice curve as you saw it when I first put it on the screen. Now, of course, the reason why this is particularly important is because what if you ask the question like, well, how far has the object traveled after 17 seconds? You don't actually need to calculate anything. You just go to the table by hitting second and then graph, and now you have all of the positions. So if we wanted to know how far it went at 15 seconds, its position was 753. And so if the question was, what is its final position? You just read it off the table. If the question is, what was its displacement? Remember, since it started at x equals 3 meters, that just means you would need to take 3 meters off of that number, meaning in 15 seconds, its displacement was 750 meters. Pretty good. So we're going to be using these functions and the idea of these functions when we're doing acceleration experiments, because we can use the idea of this function to make a graph. Okay, so I'd like you to go to the stream where the post is for today and download the sheet that says, or open up the sheet that says AP Physics Position as a Function of Time worksheet. And the first problem I'd like to focus on is B1 QRT 40, Position Equations Motion Characteristics. It says equations for the position of 4 objects executing one-dimension motion in the x direction as a function of time are given. And they ask you here a series of questions. Notice this one goes the whole way. So I would like you to focus on A, B, C, and D for right now. So take a second to pause this video. I think that part should probably take you about 5 minutes to answer those 4. For explain your reasoning here, it's important to realize you really don't need to go too nuts about it. It's a pretty basic answer as far as how you can determine the answers to A, B, C, and D. So pause this video for 5 minutes, and when you're done with those, you can hit play, and we'll go over the answers. All right, let's go over these. So part A, in a pretty straightforward way, just said, what is the initial position for object A? The initial position for object A is 5 meters. Question, of course, asks you to explain your reasoning. It's not that complicated. The initial position is the first term in the equation. That's it. It's pretty straightforward. Now, part B asks, what is the initial position for object B? And looking at the first term of the equation for object B, the initial position for object B is -5 meters. So it starts 5 meters left of the origin. And the explanation would be the same. The initial position is just the first term in the equation. Part C asks, what is the initial velocity for object C? And if we look at the second term in the equation, we can see that the initial velocity is 3 meters per second. And so the basic idea here is that the object's initial velocity is the term multiplied by the t in the position function. So whichever term is multiplied by t in the position function, that's the initial velocity. Notice also it has units of meters per second. And D asks, what is the initial velocity for object D? And the initial velocity for object D is -3 meters per second. Notice that the template for the position function says x equals x naught plus v naught t. And so the fact that the template says plus v naught t, but this term has a minus sign in front of it, that means the initial velocity is actually -3, right? Because that term v naught times t is negative, and it's not going to be negative because the time is negative, right? Because that makes no sense. So it's only negative because the initial velocity is negative. And that's it, A through D, pretty simple. Looking on in the sheet, the next two ask you for the acceleration of object A and object D. So I'd like you to pause this video here, work on E and F, and when you're finished, you could hit play and we'll go over it. Okay, so E and F asked you about the acceleration for objects A and objects D. Now, I hope you are careful about this because these, I think it's safe to say, are the trickiest problems on the sheet. The acceleration for object A is 8 meters per second squared, not 4. And the reason why is because the template for the position function says the term that's multiplied by the t squared is not A, it's 1/2 of A. And so since there's a 4 meters per second squared multiplied by the t squared in this equation, that means the acceleration is 8 meters per second squared. Whichever number is attached to the t squared is half the acceleration. So you have to multiply it by 2 to find the whole acceleration. And similarly for F, they are asking you for the acceleration for object D. The acceleration in the position function is 8 meters per second squared, but of course that's half the acceleration. And so the acceleration for object D is 16 meters per second squared. And that is because the term multiplied by the t squared is 1/2 A. All right. G, part G here, asks you, what is the position for object A at 1 second? I'd like you to take a second to pause this video, work that out. What is the position for the object at 1 second? And then write just one brief sentence on how you think you're supposed to go about answering that. Take like 3 or 4 minutes to do that. When you hit play, we'll go over it. Okay, so part G asks, what is the position for object A at 1 second? And here's our function for A. X equals 5 meters plus 3 meters per second plus 4 meters per second squared. And the answer here is that the position is 12 meters. Now, the way you get that is pretty simple. If you want to know the position at any given time, since this is a position as a function of time function, all you have to do is evaluate the function at that time. So we plug in 1 second here and 1 second here. And of course, this is easy because 1 squared is 1. And so we get 5 meters plus 3 meters per second times 1 second, which is 3 meters. And then plus 4 meters per second squared times 1 second squared. And we get 4 meters. So we have 5 meters plus 4 meters is 9 meters. And then plus 3 meters is 12 meters. And so the answer here I just wrote pretty simply, it's 12 meters. And to find the final position, you just evaluate the function at the given time. So since the given time is 1 second, you just plug that in and that's it. Okay. And the last part, pretty simple here. Last part, that's H says, what is the position for object D at 1 second? Let's just forget that because that's a repeat of the last one. That's not that hard. Let's go to I. It says, which, if any of these objects is moving at a constant velocity, and what is its velocity? take a second to pause this video and think about I. Take like 2 minutes to do that, and when you hit play, we'll go over it. Okay, so looking at the functions here, to some degree, if you really think about it, this a little bit is a game of which one of these is not like the other. And so the real question is, how can we look at these functions and tell if the object is moving at a constant velocity? Well, I think it all comes down to the answer to the following question. What is the key essential characteristic of an object moving at a constant velocity? And the answer is, if an object is moving at a constant velocity, its acceleration is 0. And if you're taking 1/2 of 0 and multiplying it by t squared, you get 0. And so if the 1/2 at squared term is 0, it's just not written down. And so the answer here is object C. And I wrote here, since the position function has no t squared term, since the position function has no t squared term, we assume there's no acceleration, and the object has a constant velocity of 3 meters per second. So the acceleration was 0, and that's why they didn't write the t squared term. And the velocity is just whatever the initial velocity is, of course, because it's not accelerating. Now, I want to just take a moment to talk about that function, because that function may look familiar to some degree. If you realize we're saying the initial position is -5, because if you're saying the initial position is -5 and then you're talking about another object and that object is at the origin, then essentially what that's saying is object C is 5 meters behind the other object. Does that sound familiar to anybody? It actually kind of sounds like a chase problem. And so the last thing I want to talk about here, and I'm actually going to post a reading about this. You should actually probably see it in your feed tomorrow, is that if you were trying to solve a chase problem, one way that you can check your answer is by using the idea of the position function. And it's especially easy because the objects are always moving at a constant velocity. So let's just use easy numbers here. Let's say we have one object moving at 2 meters per second. And so we take 2 for our initial velocity, we multiply it by x. Notice here, because I did not put a number in front of it, we're saying this object starts at the origin, so its initial position is 0, and we are not including any 1/2 at squared term because the object is not accelerating. So its position function reduces to x of t equals v naught t, and so we have 2 times t, remembering that x takes the place of t on your calculator. So let's say that object was being chased by another object that started, I don't know, let's call it 15 meters behind that object. And notice, because this object is behind, it has to be going faster. So let's say it's going 3 meters per second. Now, if you graph these two, and I'm going to make this one dotted just so we can really see the difference between them. And when we plot them and we zoom fit this graph, oh, it didn't do it enough. We got to zoom out a little. Let me just go to the window. I'm going to make the X max 50 seconds just to see, because I have no idea what the answer is. And we'll make the Y max a little bigger too. And so you'll notice this when you do this, you kind of just have to mess with it. So I'll make y max 25 and negative y max negative, or y min negative 25, and I'll graph them. All right, so they're going to cross way before 50 seconds. So now I'll move that in. And this is what you're going to have to do. You're just going to have to tinker with it until you get it to look nice. I don't know why Zoom Fit wasn't working now. That's usually pretty reliable. And so it's got to be a little taller. All right, we're almost there. I'm going to actually make y min 0 because we don't care about the negative region of this graph, obviously. And I will make my y max 30. And so notice they intersect. This y-axis is position. So the spot where they intersect is where this car catches that one. And so if we use the second and trace button, that's going to give us our calculator feature. And if we hit 5, which stands for intersect, we can see the time at which these intersect. So we click our first curve, we hit our second curve, it's going to take a guess, and it tells us that the x coordinate here, which is our time axis, is 15 seconds. So it takes 15 seconds for that object to be caught. If the problem instead asked, like, how far away from the origin does the second car catch the first car, it's 30 meters away from the origin. This is written in great detail and actually with screenshots on the calculator in this reading. So I would take a look at that because you're going to start to see chase problems a lot on homework assignments. And I didn't want to try to teach you this graphing thing before we talked about position functions. But now that we have, hopefully that will make sense and that you can use it to answer some questions. Okay. And now that we've hammered everything we need to hammer out about the position functions, we are ready to start talking about experimental design. So the basic idea here is that we need to, on the AP test, be able to describe how to design certain experiments. So they are going to tell you, here's an object. You want to measure its acceleration. Talk about how you would do that. Tell us what equipment you're going to use. Tell us how you're going to use that equipment. Tell us which data you're going to collect. And then tell us how you're going to analyze that data. Now, ordinarily, if you were in class like normal, you would actually be doing an experiment to measure the acceleration of an object. Because you are not here, we are going to have to make some modifications to the way that we do this. I am probably just going to show you the experiment we're going to do, and then I can have you do a separate one actually at home, and we'll go through that when we get to it. But for today, because this video is already getting a little long, I just want to give you some basic tips about how you could design an experiment and then talk about some equipment that could be used to do that. So the first experimental design tip, and this should be obvious, is you want to identify the quantity that's being solved for in the experiment. So in the case of this first experiment that we're trying to do here, what are they asking you to determine about this object? And in this case, it would be an object's acceleration. So you identify the quantity that is being solved for. Then you determine which physical quantities can be measured with the equipment that is provided. Now, usually they give you a little bit of leeway on the AP test because they say, assume you'll have all of the lab equipment that they would usually have in a typical high school physics lab. And so that's the equipment we're going to talk about later. So you determine what you can measure with what you have. Step 3 is to determine various other physical quantities that are already established in the problem if they are not being solved for already. And so it says here, i.e., can you set the values of certain variables in the experiment? This goes into like what we were talking about before with the graphical translations. It's like, can you make any assumptions, or can you make your life easier in any way? Yes, you can start looking at the accelerated object after it's already started moving, but can you perform the experiment in such a way where you have the object start from rest? Because if you can, that would make your life easier, because that means every time you know what the initial velocity is. So the idea is you want to already sort of like build in some assumptions about how you'll have the experiment go to make your life easy. And then the last part is to focus on the equation. You want to determine an equation that relates the unknown variable, the thing you're looking for, the quantities that you can measure, and the implied known quantities. And by implied known quantities, I mean like that the initial velocity is 0, if that's the example we're using. And I wrote here, note, this equation will allow us to solve for the unknown quantity, which is the point of the investigation. Additionally, as we already mentioned, but I'm just going to bring up again, the equation is actually super useful because all equations in this course take the form of y equals mx plus b, if it's a linear function or a quadratic function. So the idea here is that you want to identify an equation and think about how the variables in that equation can be measured. See if you can measure those things with the equipment you have, and then measure those things and make a graph. That's generally the idea here. Take a second to pause this video and write that down, and when you hit play, we'll move on. Okay, so some common lab equipment. The first common piece of lab equipment is called a Photogate. Now, we actually have these here and use them under normal circumstances. I hope you guys will be back here in a few months so you get the opportunity to do this. But a Photogate, and I'm going to have this displayed on a slide later, a Photogate measures time. So if you notice, this object has little black marks on it, and this plastic device here is called the Photogate. And in between these two arms of the Photogate, there's a little invisible laser beam. It's infrared, so it's invisible to the human eye. And when the black pieces cut that laser beam, the Photogate gets tripped. And the second that something passes through the Photogate and blocks the laser beam from going from one side to the other, the Photogate starts measuring time. Now, the nice thing about the Photogate is that if you plug into the computer how long these little black marks are, then the computer knows how long it takes a certain distance to be traveled, and it is measuring how long or how much time it takes. And so the idea is, by measuring distance, because you measured it and plugged it in, and by physically measuring the time, it does a calculation of velocity by taking the quotient of those two values. And so here's another view of a Photogate, not connected to anything. And so it's hard to see in this image, but here there's a hole on the device, and the beam comes and goes across into a detector on the other side. The next device, which we actually don't have here, you actually probably won't talk about them in experiments that much, but just in case they include it in a multiple choice question or something, is a spark timer. A spark timer is a really old device, but it's pretty useful, because what it does is it feeds this paper through the device, and the device literally makes sparks. But what's nice about it is it makes sparks at set time intervals. And so if you look at your piece of paper and you know it makes 10 sparks a second, then what you'll see is 10 dots with a certain spacing between them. And so the idea is, by measuring the spacing of the dots, considering that you know how long it takes for each dot to occur, you can measure velocity. The next piece of lab equipment, which has got to be the most versatile of all the ones I'm showing you here, is a motion detector. We actually have these here at the school too. You will definitely be seeing and talking about using this a lot. Essentially, how this works is it's a sonar device. This little piece of gold here vibrates and it makes little clicking noises. And when it makes those clicking noises, essentially what it's doing is it's sending out a sound wave. And then that sound wave bounces off of the object you're trying to measure. And then that sound wave is reflected back to the detector. And basically, by using the Doppler effect, measuring the shift in frequency that is experienced between the outgoing signal and the incoming signal, it's able to determine A, where the object is, B, how fast it's going, and if you have it connected to a computer, then it can also measure the acceleration because it does the math essentially by finding the slope of the tangent line to the velocity curve to give you values for the acceleration. So the motion sensor is crucial to mention in experimental design questions because it can measure anything you want it to measure. Oh, you need to measure position. You don't have a meter stick? Cool, use a motion sensor. Same for velocity and acceleration. And then last, they're going to mention this in multiple choice right now, but you're never going to have this in a high school physics lab, and so you won't ever mention it in experimental design questions, but sometimes they'll mention a radar gun. I'm sure you all already know this, but radar guns measure speed. And so it works based on the Doppler effect also, but instead of with sound, with light, they shoot a laser beam. The laser beam bounces off like a car and then bounces back to the radar gun. And the difference in frequencies is how it determines the speed of the object because the Doppler effect equation includes the speed of the object. And so I want you, before we go, to write this list, and that'll be it for today. The Photogate for ordinary objects is used to measure time. For any of the pieces of lab equipment that we have, like we have carts in the lab equipment that roll on these tracks and we know how long the carts are, we can use these photogates to measure the speed of an object if we put the length into the computer. Notice I also wrote known length and radius because if we input the radius of a round object that passes through the photogate, then we also know how much distance is passing through the photogate in a certain amount of time. And so that allows us to do it that way too, right? Because like if this is the photogate and there's a ball coming up through the photogate and moving this way, then the whole diameter passes through the gate. And that's the distance. The photogate measures the time, and then it just does V equals D over T. So that's the idea for the photogate. For the spark timer, as I mentioned, the spark timer measures speed by marking positions at a fixed time interval, and then you just do V equals D over T. Pretty straightforward. For the motion sensor, it can be used to measure position, velocity, or acceleration, and it does that with sound waves. And then for the radar gun, it's used to measure speeds, and it usually does that with light waves. These pieces of equipment are very important, and you definitely need to know what they measure. So take a second to pause this video and write that down. All right. Now, the next thing I really want to do is for us to dig into actually talking about how we can use all this information to design experiments. But because this video is getting a little long here, that'll be it for today. Remember, there is a test on Thursday. The topics are online in the posts for the post for last Thursday, and there are some problems on homework for you to get some practice before the test. Have a good one, everybody.